Hello everyone, my name is Snehinh Sen and I shall be your instructor for the course, A Brief Introduction to Group Theory. And today is day 1. First of all, I'd like to congratulate you all for your splendid performance in the limit examination and also for qualifying to this camp. This camp is a reward for your performance. Now, in this camp, the limit team and other students of ISI as well as professors and research scholars shall try to help your brilliant minds run faster and also help develop an insight for the beauty of pure mathematics and get motivated to study more about it. So, my topic, as it is obvious, is group theory. In this course, I shall be discussing why we need to study group theory, what exactly we need to study in group theory, and apply it to some known branches of mathematics. So the objectives of this course are to understand what groups are, the definition, some related definitions and associated examples, and then abstractly study their behavior just using those axioms and definitions. Next, we use defining properties, those axioms, to relate between two groups and also define additional properties to see how we can compare two groups based on properties and characteristics like simplicity, complexity, size, nature, and so on. Which group is included in the other, which group is smaller than the other. And then in packing, we try to pack groups like one group inside another group or put two groups together in larger class or a larger group. And finally, in connecting, we shall see how we can connect to groups, like we can connect to sets using relations and functions, how we can connect to groups by not only creating a link between them, but also respecting the additional structure given to them by assuming it is a group. Yes, groups have an additional structure as compared to sets. We shall see soon. Next, we should realize some familiar things and examples from the eye of group theory. This would allow us to use whatever results we abstractly obtain from the axioms of group theory to these examples and would simplify our task very, very much, as we should see in the very concrete example of number theory and matrices. Next, we try to classify groups and characterize them using these axioms and some theorems which we shall discover soon. Classification is perhaps the most complicated and most used part of group theory. So we should be careful. We won't be venturing too much into it, but yes, we'll do quite a bit to get the basic ideas cleared. And for characterization of groups, what we should do over here is, as I said, simplicity, then size, and other features. Are there any other features which distinctively characterizes a group? We shall see all of this and use them to classify groups. And finally, once we are ready, we shall apply a knowledge to a known region. All structure, all theorems which we shall discover and develop, we shall use it to study known regime, the regime of number theory from the eye of group theory. We'll see that it should simplify it very much and also make us realize how some theorems which are beautiful, no doubt still they are beautiful, but previously a bit hard to prove, now pretty easy. So groups. What exactly are groups? You might have heard someone say that this set is a group, or a group is a set which is structure, which I just said right now, or groups are basically sets, or this set can behave as a group. So who is right? Which one of them is right? Most of them are indeed, but to get it axiomatically correct, group have only one definition. We shall see that one. We have done a bit of prerequisite, a bit of we see the motivation behind the study of group theory. So what exactly are groups? That's the fundamental question which we should answer in this class. And also, what exactly are few basic properties of groups? Next, as the name suggests, groups in English, group of students, group of pebbles, a set of students, a set of pebbles. Synonymous, right? So our groups are basically sets. As the name suggests, it's just a collection. So a set vaguely. So are groups and sets similar, same thing? So we will also get to answer these questions like are all sets groups, are all groups sets, or what additional properties a group might satisfy to become a set, or what additional properties a set must satisfy to become a group. As I said, yes, sets satisfy some additional structural properties to become a group. Yes, we shall see that soon. But as is imperative from this talking, we should first be thorough with our set theory, at least the name aspects. So we will briefly recall set theory in the following few minutes. If you're thorough with it, you can skip it. And if you think that you have a bit of a doubt, even a bit, or some doubts, or you want to revise it once again, please do, as sets are very, very essential in the study of groups, and don't keep any space of doubt before we start studying groups. Also, there is an additional talk on set theory, a bit more detailed and comprehensive, provided by the limit team to you. You can also go through it, compact one. So now we shall be recalling set theory and see some definitions and examples of terminologies related to set theory. So now we will briefly review the important concepts of set theory. Firstly, what are sets? In a very naive way, we can say that a set is an unordered collection of well-defined objects. See the usage of the words unordered and well-defined. We have not yet said what well-defined objects are, and that's why the definition is naive. But unordered part is clear. That is, say for example in this set, a comma b comma 1 and 1 comma a comma b, both the sets are actually the same. It's just a collection. Order is not maintained inside it. So now let's see some common examples. N is the set of natural numbers. Z or Z is the set of integers. Q is the set of rational numbers, fractions, positive as well as negative. R is the set of real numbers. And this set, a bit random, is basically a collection of the objects A, B, and 1. So the objects in a set are called its elements. Now let's consider subsets and elements. A and B are two sets and A is an object. If A is an object of A, that is A was, as we said, an element of A, we say that A belongs to A. A belongs to A. Or A, capital A, contains small a. Here, small a is called an element of capital A. Similarly, when a group of elements, say all the elements of a set A are in B, that is, X is in A, an element of A, if and only if X is also an element of B, we say that A is a subset of B. Or equivalently, B is a superset of A, sub and super. And the notation, this notation is equivalent to this notation. Just note that these are mirror images of each other. Next, we say that A, the set, is empty if there does not exist. This sign without the slash over here is called exists. So this means there does not exist. So A is empty if there does not exist an A, an element of A. That is, A has no elements. We write it, represent such an empty set with the Greek letter phi. In our scope, any set which contains as a subset all the sets being considered, that is, say over here A and B, so a set which contains both A and B, all the elements of A as well as all the elements of B, is called a universal set. This concept is very relative, like there are many universal sets for two given sets. So over here, for the sake of simplicity, we won't be using a universal set, and if we should use one, we should specify which set we are using by the capital letter U is the general convention. Mod A denotes the size of A. This sign is same as the mod in integers or the absolute value of integers. This actually, in set theory, we say as the cardinality of A. But that's another deep concept, and we won't get much deep into it right now. It's not necessary. So if A is finite, the cardinality of A, or we'll say mod A, is basically the number of elements of A. For example, in our previous example, if you remember, A comma B comma 1, as there are three elements, we say mod of A comma B comma 1 set is basically 3. And say for R is infinite. Even N, all these sets are infinite. So we simply say that the cardinality is infinite for now. So note that A equal to B, two sets are equal if and only if all elements of A are elements of B as well as all elements of B are elements of A. That means A is a subset of B and B is a subset of A. You might see that many books and conventions use the notation A subset with a underline below representing equality in proper subsets, and this notation is used for proper subsets. But to avoid complications and to maintain a standard for us, we would represent this as a subset. Note that A subset of B can also imply A equal to B, as we have seen already. Next, let's consider unions, intersections, and cross products. Consider two sets A and B, subsets of a large universal set U. See, we are mentioning U over here, the universal set. Then A union B, this U-like sign, is called the union sign. This set is called the union of A and B. It's basically all elements which are either in A or in B or both. Over here, it's not an exclusive or, it's just an or. So if X is in A union B, X is in A or in B. Similarly, if X is in A intersection B, the inverted U, it's called intersection. Then X is in A as well as in B, in both A and B. So this is basically a restriction of A and B, a set contained in both of them, and this is a set which contains both A and B. So for the sake of simplicity, when we are not given a universal set, we sometimes take the union of all sets being considered as the universal set. But that's actually not well defined and we should avoid it. But we can ignore it for now. So what is the cross product, this time symbol? So the Cartesian product of A and B, represented by this cross, is basically the set of ordered pairs A comma B, says that A is in A and B is in B. This set is, as I said, is the Cartesian product of A and B, represented by this. Similar definitions can be given of family of sets, as we have seen. Suppose L is an indexing set and AL is a family, says that for each L in capital L, there is a set A small l. All sets are inside U. Then the union of L, AL, the union of the family, is defined as all sets, all elements which are present in at least one set of the family. So there exists some L belonging to L such that this symbol is such that this element is contained in an element of the family corresponding to that index. So now we come to negations and differences. See over here, negations and differences sometimes become very relative, but we fix our universal set so that no confusions arise out of this. So again, our usual assumptions, and we say A is not a subset. This sign means not a subset of B if A is not a subset of B. Similar definitions were like A is not an element of B, A is not a superset of B, or A is not empty, and loads of them. So this A complement refers to all elements which are in the universal set but not in A. So basically it's called the complement set of A. That is, A and A complement are disjoint and their union give the whole universal set. So what about the difference? This set is called the difference of A from B. My mistake. So it's basically A minus B. It's defined as the intersection of A and B complement. So these are all the elements which are in A but not in B. So it's called the difference of A from B, and it's represented by a set minus sign. This triangle represents a symmetric difference. Over here, note that A minus B is generally not B minus A. But can we bring about a symmetry over here such that that difference B is equal to B that difference A? Yes, we can. This is basically A union B minus A intersection B. This is an exclusive OR. Over here, it's either in A or in B, but not in both. That's what is represented over here. It's in A but not in B, or it's in B but not in A. So this is called the symmetric difference. Relations. So again, consider the two sets A and B, and R is a subset of the Cartesian product of A and B. Then we say R is a relation between A and B. It's just a subset. So if A contains 1 and 2 as elements, B contains E and B as elements, then R, this is a subset of A cross B, is basically a relation, a subset of A cross B. So if A comma B belongs to R, we denote it as ARB. You get it? ARB. So we shall mostly be interested in cases where B equal to A. That is, R is a subset of A cross A. So let's consider that and see a few examples or types of relations. Let R be a relation from A to A, or simply we shall call it a relation on A. We say R is reflexive if for all A belonging to A are A. That means A comma A belongs to our relation R. We call R is symmetric if ARB implies BRA. It's obvious. That means ARB and BRA, the truth value, is the same. So A comma B belongs to A if and only if B comma A belongs to A. So there is a symmetry, beautiful symmetry. But always symmetry is not good. And there are some things in the middle. But what's the extreme? Antisymmetry. So we say R is antisymmetric if for all A comma B belonging to A, ARB comma BRA implies A equal to B. So A comma B and B comma A can be elements of R if and only if A equal to B. That is ARA. So we say that R is transitive if for all A comma B comma C belonging to A, ARB BRC implies ARC. So basically this middle RBB thing goes away and ARC remains. Okay. Now if R is reflexive, symmetric and transitive, we call it to be an equivalence relation. Why? Consider equal to on real numbers. A equal to A, obvious. A equal to B implies B equal to A, again obvious. A equal to B and B equal to C tells us A equal to C. So don't you see that why this nomenclature makes sense? Let's see another example on triangles. Suppose a triangle is given. It's congruent to itself. The triangle, if triangle T1 is congruent to triangle T2, then we can also say triangle T2 is congruent to triangle T1. Obvious. Also, if triangle T1 is congruent to T2 and T2 is congruent to T3, we can say triangle T1 is congruent to T3. So again, congruency is an equivalence relation because all these three properties are being satisfied. So we have an equivalence relation and the nomenclature now makes sense. Now what about if R is reflexive, antisymmetric, and transitive, the other extreme? We call it to be an order relation. By order, consider the natural ordering of less than equal to on real numbers. A is less than equal to A for all A is obvious. Now A less than equal to B and B less than equal to A would imply A equal to B. So AR is again antisymmetric over here, the less than equal to relation. Finally, A less than equal to B and B less than equal to C implies A less than equal to C. Hence, we might say that our relation less than equal to is an order relation, and in fact it brings some order on real numbers. We can compare to real numbers. So that's quite a bit about relations. Let's now look at functions, a special type of relations. The functions are basically relations from A to B. F is called a function or a map if for all A belonging to A, there exists a unique B belonging to B such that AFB. So F is a relation between A and B and AFB. If A is related to B, then B is unique and each A has a B in B. So basically we can say that every A occurs exactly once in the subset F of A cross B. So the pretty useful alternate representation of this function is F from A to B, and FA is defined as B. The FA notation is defined to be B such that AFB. So A comma B belongs to F, then we say FA equal to B. Now let us look at functions, a special type of relations. F is called a function or a map from A to B if for all A belonging to A, there is a unique B belonging to B such that AFB or A comma B belongs to F. This is a pretty useful representation of this fact is F from A to B, this is a representation for a function, and FA, this thing is defined as B such that AFB. So basically A is called the domain of the function, B is called the codomain of the function, and all B such that there exists an A such that FA equal to B. So basically union of all FAs is what we call as the range of the function. These things are discussed in the extended set theory video. Over here we continue with this definition. So now if Fx equal to Fy implies x equal to y, we say F is injective. See, the opposite thing, that x equal to y implies fx equal to Fy is a validating condition for a function because that says that there is a unique B such that AFB. But the opposite thing is not obvious because it's also not always true. For example, there are constant functions such that it's not true. If a constant function is defined on A with a size greater than or equal to 2, then it's not injective. But yeah, if it holds, this condition holds, we say that F is injective. Now we also define F as surjective or onto. We call F an onto or a surjective map if with the range equal to codomain, that is for all B belonging to B there exists an A belonging to A such that F equal to B. Now what if a function is both injective and surjective? We say F is bijective. Now let's continue a bit more about functions. Note that if F is bijective, then you can actually find a G from B to a function G, such that GB equal to A if and only if FA equal to B. This is a very interesting fact. Basically, you have found an inverse of F, and we can say that F is invertible with inverse G. This G is usually denoted as F inverse, but what's more interesting is suppose this fact holds that F has an inverse, then also you can show that F is indeed bijective. So can you show that this condition is if and only if F is bijective, if and only if there exists an inverse? Try. If A is a subset of B, then the map FA to B defined as FA equal to A, somewhat like an identity? Not exactly an identity because B is a larger set. Maybe it's a larger set, you don't know. We say this to be an inclusion map. And if B equal to A, it's an identity map. And we denote it by 1A or identity A or sometimes IA. So indeed, our definition of bijective function with this if and only if condition can be stated as F is bijective if and only if FOG or the composition of F and G is a bijection, not just a bijection, it's an identity map, as well as that on GOF on their respective domains. FOG is defined from B to B and GOF is defined from A to A, and they are their identity maps. So what about partitions? Let S be a set and let A equal to a family. with indexing set L. So small l belongs to capital L to give us a family. We see that this family of subsets of S is exhaustive if their union is basically S. So all elements of S is there in at least one of A hells. We also say A is mutually exclusive if AJ intersection AI is empty. So AJ and AI are disjoint for all I comma j in the indexing set and I not equal to j. Otherwise, AJ intersection AI becomes AI equal to AJ. Hence, this definition of mutually exclusive and exhaustive is important, and you might have come across it in combinatorics because their partitions have a lot of use. And now, what's a partition? It's obvious over here that if it's a set is exhaustive and also mutually exclusive, we are basically splitting the set into disjoint subsets. And when I say splitting a set, it means that every element of the set is in at least one of the parts. Hence, we say that this family is a partition. A is a partition. This family here of S. So for finite sets, combinatorics has uses of partitions, and in fact, combinatorics helps us study partitions better. For example, can you try showing that the sum of sizes of all sets of an exhaustive family is greater than the size of the set? That is, for example, consider the set 1, 2, 3. Then 1, 2 and 2, 3. These two sets forming a family A is exhaustive, right? Because their union is S. But the sum of cardinalities of these two sets is basically 4, which is greater than or equal to 3, which is the size of S. So can you show this in general? And also, we can show that equality over here will hold if and only if that family is a partition. For example, 1, 2 and 3. Over here, the sum of cardinalities is 2 plus 1, which is equal to 3, which is equal to the set's cardinality. And indeed, you can show 1, 2 and 3 form a partition of S. So what about equivalence classes? We have already seen equivalence relations. So what about some classes or sets into which an equivalence relation sort of partitions a set? Let tilde represent an equivalence relation on A and let A belongs to capital A, be an element of capital A. Then the box small a, this notation represents the equivalence class of tilde containing A, or equivalently the equivalence class of A with respect to tilde. It's basically all those elements related to A. So note that A is always related to A because equivalence relations are reflexive. Hence, we can say that every equivalence class is non-empty. Indeed, if we represent the set of all families of distinct equivalence classes as box tilde, can you show that that's a partition? It's not difficult because if A is related to B, then the equivalence class of A and B are the same. That somehow with a bit of non-empty and exhaustiveness of these equivalence classes, can you show this result? A stronger result holds actually, if you think about it. Let A be a non-empty set, then S is a partition of A, if and only if it is the set box tilde for some equivalence relation box tilde. This proof is left as an exercise, non-evaluative, because it has been discussed in the set theory course. Now we come to another important concept of binary operations. A binary operation is basically an operation or a set function. We will refer to binary operations as operations on a set A. It's basically a function mapping A cross A, the cross product or the Cartesian product of A to itself. So it's if say star is an operation on A, then star is a function from A cross A to A. That's it. So an operation is a function from the cross product of a set to itself to itself. So generally, to simplify a notation, we represent star a comma v, the general notation for a function, as a star b for all a comma b in A. So it's the common notation. Whenever there is no ambiguity, we further shorten this by writing it simply as AB, by assuming that the operation is known and we don't need to write it as its imperative somehow. So we write it as an AB. Operations can be injective, surjective, or bijective, similar to a function. Can you think of an injective operation and a bijective one? Surjective is very easy. You can simply map 1 comma A to A, or A comma B to B. That's surjective, but that's neither injective or bijective. Can you think of an injective or a bijective one? Yeah, the first thing required over there is A has to be infinite. So best of luck. Now, for each A belongs to A, operations naturally induce some relation RA, right? We can say that X R A Y if and only if X comma Y equal to A. Over here, X comma Y is basically star X comma Y. You have to get it. I said operations might be ignored sometimes. It can also be ignored outside the function, like star A comma B can be represented as A comma B instead of A star B. These things become obvious when you do a bit more problems, and sometimes to avoid complications we overall omit the operation. That becomes easier instead of so many representations. But yeah, I intentionally included this X comma Y equal to A to test whether you are comfortable with this notion of switching notations for an operation. Now, we have some examples of binary operations on R that are plus, addition, minus, subtraction, cross, multiplication. But division is not an operation on R, as 1 divided by 0 is undefined. And it has to be defined if it's an operation on R. But if you remove this troublesome 0 element, R minus 0, this basically represents set of all non-zero real numbers. That division is well defined and it's an operation. So let's just check few binary operations, types of binary operations. Suppose star is an operation on A and let B be a subset of A. We say star is associative if for all A comma B comma C belonging to A star B star C is equal to A star B star C. So basically we first evaluate A star B, get the result, call it D, and then operate D and C together. We see that if we do the same thing by operating B and C together first, get E maybe, and do A star E, that's the same thing for all A comma B comma C. This notion is already familiar. You are already familiar with this notion because you have done associativity, closure, commutativity, and distributive laws from a long time, right? So again, star is called commutative if A star B is equal to B star A for all A comma B in A. We can say star can be restricted to the subset B or is B invariant if for all A comma B belonging to B, A star B belongs to B. We say that E belongs to A is the identity of star in A. If and only if for all A comma B, A belonging to A, E star A is equal to A star E is equal to A. So let's look at these two definitions together. By restricting, we mean that indeed one can say that star is also a binary operation from B cross B to B, because any element from B cross B as a subset of A cross A is mapped to B itself. So it's basically an operation on B. So that's why we say this B invariance or restricted to B. Now identity, the concept is obvious. For example, in addition, 0 is the identity as 0 plus A is equal to A plus 0 is equal to A. And in multiplication, 1 is the identity as 1 times A is equal to A times 1 is equal to A. So this notion can be a bit more abstracted from the concepts of the concrete real line or any known number systems as this definition of identity. So, now once we know that there is an identity in A, it's well defined and unique actually, we say that A is invertible in that this element small a is invertible in capital A with respect to our operation star if and only if there exists a B in capital A such that A star B is equal to B star A is equal to identity. In addition, the inverse is basically the negative of that element. For example, the inverse of 1 is minus 1. In multiplication, inverse might not be defined, though identity is defined. For example, 1 times 0, let A be 0. Then for any element, A times 0 is equal to 0 times A is equal to 0, and it's never 1. So 0 has no inverse. But can you show that R minus 0, the better behaving set which we saw before, is indeed an invertible operation? That is, for every element there is an inverse. An important note over here is if A comma star satisfies the property that star is an operation on A, this ordered pair is called an algebraic structure. Actually, algebraic structures are a bit more to do, but this, whatever we shall be doing, we shall be only engaging with one operation at a time on one or more sets. At least for each set there would be only one operation. Hence, for us, algebraic structures would mean any ordered pair A comma star. So now let us return to group theory. So now we shall be returning to groups. As we have done quite a bit of set theory, at least the necessary parts, most of them, we shall now proceed with the study of groups. We shall now see definition of groups, some related results and definitions, and some examples. Soon, once we are ready, we shall learn how group theory helps us obtain some beautiful results in number theory with ease. We shall also learn about some fundamental facts about classification and comparing between groups. But again, this question might be troubling you. Why are we going through such a trouble? Now, this question must be troubling your mind. Why are we going through such a trouble just to prove results which have already been proven, or just to do stuff which is already known? No, the thing is, group theory is not something which is already known. Actually, the things which are already known have used group theory without using the term groups, which was first coined by the genius Galois. So before that, they were groups. They studied groups, but they never thought of them as groups. So we are developing a grand unification theory to some extent, mathematics. So here we'll try to prove some abstract results which might be applied to many situations. Groups occur naturally in solving equations, general set structure, polynomials and roots, number theory, combinatorics, analysis, symmetry, other branches of algebra, physics, chemistry, and so on. The list doesn't end. It's so important. It's a fundamental structure, algebraic structure in mathematics, and perhaps one of the most well-studied ones. So you need to study groups properly, not just for mathematics or advancing in mathematics, but also to advance in related mathematical sciences. Hence, for these and many other reasons, it's difficult to put all of them in one presentation or one video. The study of groups become very essential. So let's start. So now we shall look into the definition of a group and also definitions and examples of related terminologies. A group is an algebraic structure which we just discussed, is a set with an operation on that set satisfying that this operation star is associative in G, that is bracket open A star B bracket closed then star C, is the same as doing B star C first and then pre-operating with A, that is A star bracket open B star C bracket closed. Star has an identity in G, so there is some element E in G says that for any other element A or even E itself, A star E is equal to E star A is equal to A, and each element of G is invertible with respect to star, which means that every element, say A is an element and E is the known identity, then there is another element B in the group such that A star B is equal to B star A is equal to E. That's the concept of invertibility. Note that in the definition of the group, we have never used the term commutativity or whether the group operation commutes. But it might happen that the group operation is commuting. In that case, we say that the group is abelian. But there are non-abelian groups as well. You'll come across them a bit later. So now let us look at some examples of groups. The following are examples of few abelian groups which are also infinite. Z plus is the group of integers. Note that addition, as you already know, is closed in integers as well as associative. So what remains to see is whether it has an identity. Yes, it does. It's 0. And inverses. Yes, if A is an element, its inverse with respect to addition is minus A. So similarly, you can show that these are also groups, as addition is always familiar. And over here, this R square is the set of all vectors in the plane. So this is basically a set of all vectors with vector addition, and these are normal number additions. As you advance in linear algebra, you will realize that vector addition is nothing but normal addition over two related things, that are the two elements of R square. So these are all additive groups. Now let us look at a group which is not additive. For example, Q plus comma cross. Cross is multiplication over here, and Q plus represents all positive rational numbers. Note that multiplication is again associative, and if A and B are two elements of Q plus, then AB is also an element of Q plus, as it's both rational and positive. So now we also have 1 in Q plus. 1 is a positive rational number which satisfies that A times 1 is equal to 1 times A is equal to A for any element A in Q plus. So we also have an identity. And what about if we have another A greater than 0 and in rationals? Then 1 by A turns out to be the inverse of Q, that element. Because A times 1 by A is equal to 1 by A times A is equal to 1. So we also have an inverse. Hence, Q plus comma cross is indeed a group. So a similar proof can be shown for R plus comma cross, and extending this idea to negatives as well, and realizing the fact that the inverses of negatives are negatives itself. Q minus 0, the set of all non-zero rational numbers, along with multiplication, turns out to be a group. Now let us look at some non-standard sets or some derived sets over here. M in R is the set of all n cross n matrices with matrix addition plus in reals. That's again a group, because if A is a matrix, then minus A turns out to be the inverse. If the 0 matrix is the identity, and matrix addition is both closed and associative in the set of real matrices. Similarly, Mn cross M represents the set of all n cross m matrices over Z or Z, or the set of integers over here. And that, along with matrix addition in this set, is again a group. In fact, over here you could have replaced it with any of these sets, and over here as well. But these are all matrix additions. What about matrix multiplication? No, matrix multiplication is not a group because the 0 matrix is not invertible. But even if we remove the 0 matrix, it turns out it's not a not that simple like reals that removing the zero gives us a group in multiplication. It's a bit advanced, and in fact, as I was telling you, these are all abelian. If we tamper with the matrix multiplication a bit and remove some very disturbing elements from the set, we'll see that it indeed is our first non-abelian group, although infinite. So I gave you a few ideas about how to construct groups from a standard sets with standard operations. Think of at least three other such groups. And as I told you, an example of a non-abelian group, just hand waving and just few words, we'll concretely see how to come up with the non-abelian group of matrices. And for finite groups, we have to wait a bit. Note, there are also groups which are finite as well as abelian, and some which are finite as well as non-abelian, but that would take some time. So for now, if there is no ambiguity with which operation we are considering, we shall skip star from the definition of the group and represent the group only by the set, and A star B would be written as AB, just for simplicity. So let G be a group. An element of a group is basically an element of the set. A subset S of G is called a subgroup of G if star the operation is S invariant. That is, star is also an operation in S. Star defined from S cross S to S when restricted is also a function. E, the identity of G, is in S. This means that the identity which we were speaking about of the group is also present in our set S. So again, if G is an element of S, then G inverse is also an element of S. That means it's closed under inverses. So whenever I have an element, its inverse is also in our set. If all these three properties are satisfied, we say that a subset is a group or a subgroup specifically. You know why this terminology comes? I just told you. Indeed, if you consider S comma star, it turns out to be a group. So we have a few examples over here. Z comma plus, the additive group of integers, is a subgroup of the additive group of real numbers. It's easy. Z is a subset of R, and it is a group. We saw just now. Hence, it is a subgroup. Now let's see a subgroup of the matrices. M and R has a special subset called the equator. You might have heard about the term trace. Trace of a matrix, a square matrix, is basically the sum of all main diagonal elements, that is A11 plus A22 plus dot 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 ANN. The sum is called trace. If this trace is 0, the set of all trace 0 matrices is called the equator of the group MNR, additive group MNR. This equator turns out to be a subgroup. Can you check it? It's pretty simple because trace splits on addition, as it's obvious. Notationally, we would represent that S is a subgroup of G as S less than equal to G. Yes, this is the same less than equal to sign as in the order of real numbers. Actually, this justifies another thing. Consider this example, Z plus and R plus. We also have Q plus, and Z is a subset of Q as well, and Q is a subset of R. So it turns out that Z plus is a subset of Q plus. In fact, a subgroup of Q plus, and Q plus is a subgroup of R plus. So we have, if A less than equal to B and B less than equal to C as subgroups, then A less than equal to C. Over here we have Z less than equal to Q, Q less than equal to R. Just those two facts would imply Z less than equal to R. That justifies our nomenclature or notation which we have used over here. So now let us look at powers of elements. So again, it's a group with identity E, and A and B are elements of the group. Then E power 1 is basically A. It makes sense, right? A power n is recursively defined as A times A power n minus 1. Note that over here we have done pre-multiplication, but you know what? It can be shown that powers commute. It's pretty easy, right? We'll soon see how. Again, A to the power minus 1 is basically A inverse. Over here it's power, and over here it's the inverse. Same notation, so there's no point considering it to be the same thing. And a power minus n is simply defined as a power minus 1 whole power n. Note that you can also write it as a power n whole power minus 1. It's the same thing. In fact, we'll see that a very similar and in fact a stronger result holds soon. And if n is 0, then a power 0 is basically the identity. This makes sense because if x is non-zero, then x power 0 in real numbers with multiplication is considered to be 1, the identity in that multiplication operation. And in addition, a power 0 is basically 0 times a. That's 0, which is the additive identity. So let's look at some examples over here. Z comma plus in the additive group of integers, a power n, as I said, is basically n times a. You're adding a n times. And you can check it from the operation. So 2 power 4, though it looks like 16 in additive group of integers, it's basically 8 because it's 4 times 2. In R plus, the positive real numbers with multiplication, 2 power 4 means the standard thing, it's 16. Okay, can you think of something? Can integers be turned into a multiplicative group? The easy answer is no, because the second positive element 2 has no inverse in integers with the defined multiplication. So for the sake of notational convenience, we might refer to the identity as E or 1 without even defining it. We know there is an identity because G is a group, and we might write it as E or 1 depending on the situation. Now let us come to order. When we say order of real numbers, we don't just mean some like arranging or some permutation. Order basically refers to the size of real numbers and arranging them based on their size. Our natural concept of order comes from how large a number is. And we say x is greater than y if x is larger than y in our general notion. So, in the context of group theory as well, order refers to size. Let G comma star be a group with identity 1 and A be an element of G. The order of the group G is defined as the size of G, the cardinality of G, as we had seen in set theory. So if the cardinality is finite, we just simply say G is a finite group and order of G is the size. Say G has n elements, then order of G is n. Otherwise, we say G is an infinite group. This part is pretty simple and it's basically the cardinality. Till now, if you have noticed, we have only dealt with infinite groups. We will shortly see a few finite ones, but before that, we consider a theorem. Actually, two. So now let us look at some properties of power. G comma star be a group with identity 1, A and B are elements of G, and P, Q be integers. Then A power P, A power Q is equal to A power P plus Q. Can you prove it with induction? It's not difficult. And indeed, it's quite, what should I say, obvious when you look for real numbers or rational multiplicative groups or even additive groups. It becomes a bit difficult in the abstract sense. But you know what? We assume those results in reals or rationals or integers with additions. Those also have been proven sometime by assuming some axioms. Over here we have some different sets of axioms. So try your best to prove these. Next, A power P to the power Q is equal to A power Q to the power P is equal to A power PQ. PQ is also an integer. This can also be proven with induction and some manipulation of the axioms. Try. And the last one, it's easy. A square B square is equal to AB whole square implies A and B commute. So does this mean that it just for two elements A square B square is equal to AB square the group is abelian? Not at all. It just says that A and B commute. For an abelian group, all elements should commute. So over here, this is pretty simple, as if you cancel A from the left and B from the right on both sides, it turns out that the LHS is AB and the RHS is BA. So our result is indeed true. G is a group with identity, and if G is finite, then we need to show that there is a power of A which is 1. So this is interesting. Not only this tells that every element 1 is a power of every element, but this also tells us that every element has one of its power as its inverse. I must clarify my previous point over here. What I meant is the inverse. If n is 1, then A is identity, and we are done. That A is the inverse of itself. Otherwise, A power n minus 1 turns out to be the inverse of A. Can you check it? Yes. So suppose the size of G is m. We consider the numbers a squared dot 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 a power m plus 1. By pigeonhole principle, there exists p lesser than q. Why? There are m plus 1 elements over here, and we know that the group has m elements, so two elements have to be equal over here. So there is a p less than q, not even equal to, such that a power p is equal to a power q. Quite simple, right? So indeed, a power q minus p is equal to 1, and q minus p turns out to be a natural number, as p less than q and both of them are integers. This is indeed a pretty important result, as we shall see soon. But can this result be refined? Over here we have no idea what n is. Can we do something and some jugglery to see what exactly n is? No, it's difficult to realize what exactly n is. It depends on the element. But all such n's satisfy a beautiful property. You can show that the set of all elements such that a power n equal to 1 contains m, the size of the group. So any element raised to the size of the group is 1. You might like to use Bezout's lemma and the well ordering of n over here, but this is an exercise for you. Try it yourself. Later on, in the next class, we shall see a more elegant proof of this fact, the second one, after we have developed some tools. The previous proof gives us a motivation. When was the first time the power of an element hit 1? Or does it ever hit 1? Doesn't this tell us something about the size or nature of the element? Yes, it does. So we are motivated to define the order of an element. Suppose there is a power which is 1, then the order of the element A is defined as the minimum of these powers such that it is 1. Note that this is a subset of natural numbers and non-empty, hence this can be thought of. The minimum is well defined because of well ordering principle of natural numbers. Now suppose this set is phi. Suppose there does not exist a natural number such that a n equal to 1. We say the order is undefined. We don't use the concept infinity over here generally because it's a bit vague. However, this basically says that the element is pretty large, as it can't be contained in 1, no matter how large a power we take. So this is a very interesting result, right, in groups. If G is finite, then every element has a defined size or order. This is what our previous theorem tells us. We represent the order as same as a group OA, or simply mod A. So before we proceed further, let us look at some properties of the order of elements. Let G be a group and 1 be an identity and A be an element of this fine element with a finite order, say O. Then A power n is equal to 1. That is, A power n becomes the identity if and only if the order of A divides n. So let us look at the proof over here. We have used the properties of power. So this first part is pretty clear, I hope, and let's look at the second part now. Suppose O does not divide n. What we are doing over here is not proving A power n equal to 1 implies order divides n. That could have been proven, but we are doing something else, an equivalent statement, the contrapositive. That is, if O does not divide n, then A power n is not equal to 1. The concept of contrapositive must be known to you, and it's a very important mathematics. So just go through this proof, it's not difficult. I hope you have gone through the proof and understood it. Just one point, a power r not equal to 1. This is by the definition of order, because order is the minimum element and r is lesser than o and not 0. If it's 0, then o divides n. So r is not 0 and it's lesser than o, so it can't be 1. Otherwise it contradicts the definition of our order and would say that o is not the order over here. Hence our claim was true. So this beautiful result has two corollaries over here. Let's look at them. In a finite group, the order of any element divides the order of the group. This was the second theorem, the exercise, and the previous one. Basically over here we get a power, the order of the group is 0, is identity. Basically we get that a power, the order of the group is the identity. So the previous theorem would imply order of A divides order of G. In fact, it turns out that the set of all elements which sort of sends A to 1, set of all powers which sends A to 1, is all multiples of the order, positive as well as negatives. And this can be treated as a group. Think of it once, it's not difficult. So now we come to a different type of group. It's called the cyclic group. Let G be a group and 1. Then the group generated by A, represented by this greater than, lesser than sign and A in between, is basically all powers of A. This is abelian. It's not difficult to see, as A power P times A power Q is A power P plus Q, which is equal to A power Q plus P, as P plus Q is equal to Q plus P in integers, which is equal to A power Q, A power P. Hence it's abelian and it's a subgroup. Subgroup part isn't difficult, right? You can show it. So we now also have a new type of group, an abelian subgroup of G, which we shall be calling the cyclic subgroup, generated by A. Note that it only depends on A, the subgroup only depends on A. So a natural question arises. So every group contains a cyclic or an abelian subgroup? Indeed it does. Abelian part is pretty easy, right? One is abelian and one in fact is trivially cyclic, but it also contains a non-trivial abelian and cyclic group, and this is what we have just shown. If A, order of A is finite, then the size of the cyclic group turns out to be the order of A. Otherwise it's infinity, as A power P is never equal to A power Q for two P and Q integers. So this is a very interesting thing, and just go about it and think why order of A is the size of the cyclic group for finite order. For infinite it's easy to see. Now this next property tells us the order of a power of A in terms of the order of A. Just go through it once, it's not difficult. This sign over here represents GCD, or the greatest common divisor, or what you might have heard as highest common factor. So basically it says that if K is the GCD, then K divides order of A, and the quotient which you get by dividing order of A by K is the order of A power n. So if n and order of A are co-prime, that is the GCD is 1, it turns out that order of A power n is simply order of A. This is also easy. Just try to prove this. If order of A is undefined, so is order of A power K. Also try to prove this one. This is relatively easier. In fact, if G turns out to be the cyclic group generated by A, we call G is a cyclic group. So abstractly take an element and just say that its order is, say, n. Then define G as the cyclic subgroup, or over here the cyclic group generated by A, all the powers of A. It turns out It's a finite group of order n, as we just saw here, and it's abelian. So we have the first abstract, not concrete, example, or rather example of family of abstract finite groups. All of them are abelian over here. So let's look at some relations and unique things in a group. These laws which are given over here are not difficult to prove. The cancellation law, we have been using it right from the start, but we never mentioned it. But it's a result of just the axioms of group. Similarly, the law of inverses, you might have seen this for matrices, but now you have it in a general framework. Similarly, general associativity, something which we have been using in multiplication, addition, matrices, and so on from a long time. But now it's actually a theorem or a result of those group axioms. Now, what about identity and inverses of elements? It turns out they are unique. If we have an element, its inverse is unique. The identity of the group is also unique. So, can you just prove these two facts? These are not difficult, just require some patience and a good understanding of what groups are. The involution law is also pretty obvious, right? What's the inverse of 2 in the additive group of integers? It's minus 2. What's the inverse of minus 2? It's again 2. So it says that the inverse of an element is that element itself. So these 6 results, pretty beautiful and seemingly pretty advanced, are just simple corollaries of the axioms of group theory. So you do realize now, right, how 3 axioms and a few definitions can actually lead us to very beautiful and surprising results in mathematics. That's the beauty of mathematics, pure as well as applied. So now let us summarize what we have done till now. We have seen a brief review of set theory with functions, relations, and so on. We have defined groups and subgroups with examples. We have defined orders of elements as well as orders of groups with examples. Note that the order of subgroups is the same as order of groups because every subgroup is a group. We have seen theorems and related results to these definitions. We have seen the definition of a cyclic group, which was a first finite group. Let me ask you something. Suppose the order of A is undefined. Then what's the cyclic group? It's an abelian infinite group. And it has a structure very, very similar to Z, or the set of integers, right? Finally, we found a finite group. This is the cyclic group. A bit abstractly, but yes, we have an example of finite group now. So now we are ready for a few more example of groups, which would include our previously the stated matrix example, as well as method to concretely construct finite groups. The cyclic group can be constructed concretely from what we know and some standard sets. So now let's briefly look into our first example, the example of matrices. So you might see my handwriting is not so good, so I would be clearly stating all the points what I have written over here. And if you have any doubt, you're free to ask me during the Q&A session. But I hope I would be able to clear all of the handwriting related doubts over here. So you already know multiplication of matrices in 3 cross 3 matrices and 2 cross 2 matrices, right? It's the same thing for n cross n or indeed general matrices with some compatibility. But we'll only deal with square matrices for this course. So let's look at multiplication in MNR and determinants. As we already know that multiplication goes like, suppose we multiply this matrix with this one, it's like we go this, for the first element we go this row and this column. For the second element in the first row we go this row and this column. So basically if Aij are the elements of A, I represents row and J the column, and similarly Bij are the elements of B, then Cij, the ijth element of C, the element in the ith row and the jth column, is defined as the sum of the products aik times bkj, k equal to 1 to n. This is the definition of Cij. So that's how we define matrix multiplication, and I hope all of you are comfortable with it already, because it was also a part of our syllabus in the examination. So now we abstractly extend the definition of determinants to n dimensions in MNR. We already know it for 2 and 3. You might have also seen it for 4, but let's consider it for n. The minor obtained by deleting ith row and jth column is represented as aij. What's that? For example, a12 over here. We delete the first row 1, 2, 3, 4 and the second column. So it's basically this matrix 2, 4, 5, 5, 3, 2, 7, 3, 1. This is called the minor obtained by deleting the first row and the second column. So similarly, we represent minors as aij. Inductively, we define determinant of A as A1k times the determinant of A, capital A, that is the minor 1k. This mod over here is the determinant, and I've just written it to compactify a summation notation, times minus 1 whole to the power k plus 1. This thing is important. So now this is the definition of determinant. As you see that the order of any minor is 1 less than the order of the original matrix, as we are deleting one row and one column. So it's n minus 1 plus n minus 1 matrix. So this gives an inductive definition, as we already know determinants for 3 cross 3. This is a bit inductive. In fact, you might already have seen it that the definition of 3 cross 3 depends on the definition of determinant in 2 cross 2, and it's also inductive. So this is how we define determinants for now. So let us look at an example of determinants. This matrix over here is called A. So our notion of determinant says that determinant of A is basically 1. Note over here, we are going in the first row. So it's 1 times the determinant of this thing, 3, 4, 5, 4, 3, 2, 5, 3, 1, plus minus 1, because it's minus 1 to the k plus 1 and k equal to 2, this becomes minus 1, times 2, this element, times the minor 2, 4, 5, 5, 3, 2, 7, 5, 3, 1, obtained by deleting 1, 2, 3, 4 and 2, 3, 4, 5. Similarly, we go on adding other determinants, and this determinant of A is basically inductively the sum of some multiples of the determinants of these matrices. And you can find these. You already know it for 3 cross 3. Interestingly, a few properties of determinant in M3R continue to hold in MNR. First of all, determinant is linear in rows. So basically, you can split a row as P plus CQ. The determinant, if the ith row is P plus CQ, then the determinant of this matrix turns out to be the determinant of P in the ith row, keeping all other rows the same as in this one, plus C times the determinant of Q in the ith row times plus C times the determinant of Q in the ith row, keeping all other elements same as this one. So this is basically the composition of two facts, that is determinant of P plus Q, set C equal to 1, and determinant of P plus Q is determinant of P in the ith row plus determinant of Q in the ith row. Note that P and Q are over here row vectors, or basically a 1 cross n matrix. So it's important to note these properties. And also the second one which I was saying is multiplication. So set P equal to 0, so it says that determinant of CQ. So if the ith row is CQ, then determinant of that matrix with CQ in the ith row is the same as C times the determinant of Q in the ith row. So we can take out one factor from a row in the determinant. Next, determinant of IN turns out to be 1. So IN over here is the nth order identity matrix. So IN over here is the nth order identity matrix, 1 in the diagonals and 0 elsewhere. So its determinant turns out to be 1, and it inductively follows. So determinant is preserved if we add multiple of a row or transpose the matrix. That is, if we take a row, multiply it with some constant and add it to some other row, keeping the original row fixed and just changing the other row with a constant times another row added to it, we find that the determinant remains the same. The transpose is similar. We are basically the determinant of A is equal to determinant of A transpose. So let us look at the multiplication fact once more. Let suppose consider our previous A matrix over here, and we need to find its determinant. Instead of finding the determinant directly, we can simply subtract the first row from the second row. So it becomes the determinant of 1, 2, 3, 4, 1, 1, 1, 1, 5, 4, 3, 2, 7, 5, 3, 1. Note that this row would change in that case. So this might be a bit hard if you're doing it for the first time, but note that it's the same thing in 3 cross 3 matrices or any other determinant which you might have done before. So it's just a generalization to a higher dimension. So determinant can be obtained by expanding along any row or any column using rules as in 3 cross 3. The minor rule, the sign rule and all. You already know it, but it's good if we follow a certain convention and use our notation for the expansion of determinants. Determinant reverses sign if we interchange two rows. Yeah, this is true in 3 cross 3 and also in n cross n, and this is a result of all these. You can show it. So determinant of AB, interestingly, turns out to be the determinant of A times determinant of B. Also, invertibility. The condition of invertibility in 3 cross 3 was determinant of A is non-zero. This also holds in n cross n, and this can be shown. So determinant of A is not equal to 0 if and only if there exists some matrix in M and R such that AM is equal to MA is equal to IN. This condition, the second condition over here, is called the invertibility condition. So determinant A non-zero implies the matrix is invertible, and M is called A inverse. So it's similar to M3R, and you already know a bit of it. So I won't be going much deep into determinants and matrices, but it's required if you want to do group theory properly. In this course also we won't be using much of it, but if you want, you can refer to the beautiful book on algebra by Michael Artin, where it discusses matrices and determinant very beautifully, and also some additional concepts which we haven't discussed yet in the first chapter. Note that multiplication of matrices is associative. You can prove it. There is an identity IN. Is there some restricted condition for invertibility such that it becomes a group? It turns out there is indeed. The matrix groups of our interest is what we will deal with now. Till now we have only seen abelian groups, and this is because most of them were additive or part of a field. Field is an algebraic structure which is like two groups in the same set. It's a bit advanced and difficult. We won't be dealing with it, but fields assure commutativity, or what results in abelian groups. So at the end of the course, I'll refer few books on abstract algebra and in general algebra. There you can read about fields and so on, at least the definitions, so that you can generalize some concepts or and learn a bit more about group theory than what we have discussed in the course. It's very little what we'll be able to discuss in 3 or 4 hours. So let's look at the definition of a non-abelian group, the first one for us. The general linear group of order n, GLN, over reals is defined as GLNR, the set of all invertible matrices in MNR. But wait, we need to prove it, right? This is a group. We know associativity, closure, and identity already. Still, closure of matrices we know, but closure of invertible matrices? This determinant A into determinant B is equal to determinant AB property. This determinant A into determinant B is equal to determinant AB property says that it is indeed closed. We have some properties over here. So note that determinant is a function from M and R to R, and indeed by restriction it's a function of GL and R to R. So this property holds. So AB as determinant AB turns out to be non-zero. AB is indeed invertible, so AB is in GL and R. So associativity and multiplicativity. So associativity and identity hold because identity matrix is invertible as it's one and its inverse as itself. And associativity of matrix multiplication is something which is a bit general. So for inverses, It turns out the determinant of A inverse is also non-zero. It exists. First of all, A inverse exists when A has a non-zero determinant, and if it exists, A inverse also has a determinant not equal to 0. So it turns out A inverse is also in GL and R. You can look at the proof over here. We have a subset of MNR behaving as a group. Though MNR is not a group under multiplication, a subset of MNR is behaving as a group. And that's a non-abelian group. You have an example over here for n equal to 2, the smallest possible case. So if A is equal to 1, 0, 0, 2 and B is equal to 1, 1, 0, 2 over here, it turns out both of them have a determinant 2 not equal to 0. So both of them are in GL2R, and AB is not equal to BL. You can look over here. So GL2R is non-abelian. Can you find general examples for GL and R? It's not difficult. It's pretty easy to show that. You already know that matrix multiplication is not commutative. But what about this subset? Are elements of this subset also non-commutative? Just try it. We now look at a special subgroup of GL and R. All matrices with determinant 1. This isn't hard to see that it is a subgroup, as determinant A, determinant B is equal to 1 implies determinant A inverse and determinant AB is equal to 1. Right? So all these properties hold, and just rigorously try to show that this indeed is a subgroup, and it's called a special linear group of order n, SLNR. For the interested readers, I leave a note over here. If you already know what fields are or what rings are, GLNF, MNF, SLNF, and in fact it's SLNR, MNR, all these make sense. And in fact, MNR, all these make sense where R is a ring. But this won't be required in this course and might require a bit more knowledge about groups and other algebraic structures. Come to a second example. This example is on modular groups or group of remainders. So we introduce a few notations, and also we introduce the notion of modular arithmetic or working with remainders in integers. So let A, B, C, D be integers and n be a natural number. We say A is congruent to B mod n. This notation reads as A is congruent to B mod n if and only if n divides the difference A minus B. So if A is congruent to B mod n, we might assume that they represent the same element mod n. So this is something which we will come back again, but that's the basic idea. So if A and B are the same elements mod n and C and D are the same elements, then can you show that the sum or the notion of sum which we knew in integers is well defined over here as well? Yes, it is indeed, as A minus B and C minus D are both divisible by n. A plus C minus B minus D is also divisible by n, and that implies A plus C is congruent to B plus D mod n. So can we also show that the notion of product in integers is well defined when we find an equivalent in mod n? Yes, you can show it. There's a hint given over here. Try it out. So let's have a few more properties. A is congruent to A plus Kn mod n. So this is true, as the difference over here is minus Kn and n divides minus Kn for all Kn integers. Indeed, if A is equal to 0, we have any multiple of n, Kn is congruent to 0 mod n. So over here you might have noted I didn't say 0 is congruent to Kn mod n, which is the direct result of this statement. However, I inverted and said Kn is congruent to 0 mod n. Indeed, this relation over here of modulo is both symmetric and reflexive. Reflexivity holds over here as A is congruent to A mod n, is pretty easy to see as the n divides 0 for all n. And again, A is congruent to B mod n implies n divides A minus B. That also implies n divides minus of A minus B. That is B minus A. So B is congruent to A mod n. Hence, 0 is congruent to Kn mod n and Kn is congruent to 0 mod n is the same thing, and we should use it equivalently over here. So now let us look at the notion of division in modular arithmetic. Firstly, note that we have already dealt with addition, multiplication, and as we have no addition, we can also deal with subtraction over there. But what about division? Division is not well defined in integers. Yes, you can always write 1 by 2, but 1 by 2 is not an integer. But it should be if division was well defined. So, can we define the notion of division in modular arithmetic? Suppose the GCD of A and N is 1. Then by Bezout's lemma, there exists x and y belonging to integers such that ax plus ny is equal to 1. Equivalently, there exists an integer x such that ax is congruent to 1 mod n. Take mod n over here as ax minus 1 is congruent to 0 mod n, or ax minus 1 is divisible by n. You can write this. So, indeed, this property says that if we multiply by x and take mod n, it's the same as dividing by a and taking mod n. So division does make sense when the GCD is 1. But if the GCD is greater than 1, this result makes no sense, as there will not exist some x such that ax minus 1 is divisible by n. So n does not divide ax minus 1 for all x belonging to integers over here. So if the GCD is greater than 1, division does not make sense. So all this discussion leads us to state that in modular arithmetic, we see A is invertible, or division by A makes sense, or A is a unit. This is the term we use if the GCD of A and N is 1, and it's an if and only if condition. So this is a very trivial result. It states the uniqueness of inverses for equivalent elements. A and B are equivalent, x is the inverse of A and y is the inverse of B. Then x and y are equivalent mod n. That's our claim. Try to prove it, it's not difficult. So now let us look at some further properties of modulo. Just go through these properties. I'll just state two of them in details. First of all, look at this one. B is congruent to C mod n. If A is congruent to B mod n is known, and we also have additionally B is congruent to C mod n, then A is congruent to C mod n. This is pretty simple to prove, as n divides A minus B and n divides B minus C, and also divides the sum. So n divides A minus B plus B minus C, which implies n divides A minus C, or A is congruent to C mod n. So indeed our relation over here is transitive, but we already knew that it's reflexive and symmetric, hence it's an equivalent relation. So we'll do some tricks with the equivalence classes over here. That is, all elements which are equivalent mod n and form a group. So remaining all properties are pretty simple to prove. We'll just look at this last property once again. So if x comma n is d, that is GCD is d, not 1, then can we invert this fact that if a is congruent to b and x is a random integer, we have seen over here that ax is congruent to bx mod n, as n divides a minus b and also divides ax minus bx. So can we invert this fact? Yes, not exactly, but to some extent. Suppose we know this, then ax is congruent to bx mod n implies n divides ax minus bx. So n divides x times a minus b. But n and x have a factor, the greatest factor which n and x can have in common is d. So if we divide by d, then the remaining part of n must divide a minus b. This is easy to see, right? So if this is true, we can also write a is congruent to b mod n naught, where n naught is the remaining part, that is n by d. Try to prove this rigorously. So now we look at the equivalence classes and do some jugglery to create a group again. So first of all, we denote the equivalence classes as a bar instead of the regular box notation for all a in Z. So note that there is always an integer between 0 and n, 0 inclusive and not inclusive, such that a bar is the same as r bar. This is basically Euclid's division lemma, and you know it, right? So indeed, if we consider the set of all r bars such that r is less than n but non-negative, we call this set as Zn, and this is a partitioning of Z, right? Because we already saw that every a belongs to a bar, and a bar is same as sum of this r bar. Note that this also has an additive group structure. We have already seen addition makes sense. So let's look at it once again. Closure and associativity follows from the basic properties of addition and partition. Try to prove closure. It's pretty simple, because if the sum of two elements over here exceeds n, then just do minus n, otherwise you already have an element less than n. And associativity is a property of addition, so it transitively holds over here. Finally, A inverse over here. If we have identity 0, then 0's inverse is 0. Otherwise, if it's greater than 0, then n minus a is also greater than 0. And these two elements, a and n minus a, the sum of them is again 0, the equivalence class of 0, right? But we also note one thing over here. This sum is commutative. So bar a plus bar n minus a is the same as bar n minus a plus bar a, as our operation here is commutative. So we have an abelian group and it's finite, right? It has only n elements. So we have our first concrete finite abelian group. So this is an achievement which we said a concrete, or so using some standard sets we can achieve some finite groups as well. So for notational convenience we just ignored the bar and we represent the notation as plus n like this, and which can be also written as plus to save ink or notation. So if there is no ambiguity with the n, we simply ignore it. Is Zn also group in multiplication? We just saw that multiplication has a sense over here and it's well defined. But it's not a group, right? Because 0 is over here and 0 is not invertible, right? Come on. So basically we had a multiplication again, but it's still not a group. Can we do something like remove the 0 or something which we did in real numbers? Even if we remove the 0 and suppose n is not a prime, then n has a divisor, a proper divisor which is not 1 or n. And that element is not invertible, right? We just saw if the GCD of two elements is not 1, it's not invertible. So what can we do if n is not a prime? If n is a prime, we see that indeed removing 0 gives us a group in multiplication because all of the elements have GCD 1. But if it's not a prime, then well, we define a specific subset as the set of all elements which have a GCD 1, and we call it the set of units. Indeed, each element in Zn star has its inverse in Zn star as well, because r comma n is 1, and if rx is 1 mod n, then x comma n is also 1. We consider the equivalence classes and we can prove this rigorously. So this subset behaves as a multiplicative group indeed. Try to prove it once. We'll come back to it later on. But is it a subgroup? The simple answer is no. Why? Now we just pause till future applications. Go through this part properly before the next class. At the end of the next class, we'll use all these, our application of group theory, when we'll study number theory. So we'll prove some beautiful results using these properties and some more tools which we'll develop soon. And just answer these two questions. Can you show that Zn, the additive group, is cyclic indeed with 1 as the generator? But what about Zn star? When is it cyclic? We have already seen that it's a group. Not proved it directly, but we have stated it. But when is it cyclic? Just think about it. So for now, we'll pause and now we go to our next example. So we come to our next example, which is the group of symmetries. This is our final example. So firstly, we note that wherever there is symmetry, there is something related to groups or a group structure over there. We'll not go much deep into it. We'll just look at symmetries of functions. So composition of bijective functions. You might already know that it's bijective, right? We denote the set of bijective functions on a set A to itself as bij A. So bij A is defined as basically the set of all bijective functions. This composition is an operation which returns an object back. In general, this is just generic definition, just for notation. And note that if f is bijective, then f inverse is also bijective, right? So h is equal to g inverse of f inverse is a function. We don't know whether it's bijective now. We have to prove that this p, the composition of f and g, if f and g are bijective, is bijective. So we have h. Indeed, h behaves like an inverse, right? HOP and POA are both 1A or the identity of A. Try to prove it. We have proved this over here for H O P. Try to prove it for PH. So if we have an inverse, we know that this is an equivalent condition for the function to be bijective. Hence, a function P as well as a function H are bijective. And indeed, it turns out the inverse of P is H. So H is equal to P inverse. So the composition operation is closed in the set bij A. And composition is associative. You already know it, that the composition operation is associative. We have seen over here that even inverses are there in bij A. So it's an associative closed operation with inverses and also the identity 1A. So indeed, bij A is a group under composition. So we have a new group, right? Isn't it amazing? Just with function compositions, we have a group, and this is a new operation altogether. Till now we only saw multiplication and addition under different circumstances, but this is composition, a different function. But is it actually completely new? Indeed, when you do linear algebra later on, you'll realize that multiplication of matrices is basically composition of functions. But I'll not go deep into it. If you are interested, you can search it up on the net. Let A be a finite set of size n and B is equal to bij A, the set of bijections of B. Suppose C is another finite set of size n. So A and C are both of the same size. So this means that because it's a finite set, we can order the elements as A of A as A1, A2, dot 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 An, and C as C1, C2, dot 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 Cn. Now consider the function C, which sends A1 to C1, A2 to C2, dot 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 An to Cn. That's a bijection, right? It's surjective as well as injective. So we can say that every element of bij A or B has an equivalent element in bij C with respect to C. Just think about it once. Basically, suppose we have an element, say, in bij A, A1 goes to A2, A2 goes to A3, A3 goes to A1, and remaining all the elements are fixed, that is A4 to A4 and dot 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 till An to An. This is the same as C1 goes to C2, C2 goes to C3, and C3 goes to C1, and the remaining elements are fixed in with C. This is with respect to C, right? So these two groups behave similarly. By similar, we haven't yet compared or learned linking or comparing groups. But it does make sense to say that these two groups are actually the same, bij A and bij C. Just think about it once. I'll clear your doubts in the doubt clearing session if you have any. But it's similar, and we'll see exactly how similar they are in the next class. But bij A and bij C, you can say, are basically the same sets and same groups. So it's a renaming, as I said. A1 is renamed as C1. AI is renamed as CI. So bij A and bij C are the same sets actually. So the group of bijections of similar size sets behave similarly. The set doesn't matter, the size matters when we are looking into bij of that set. We call it the symmetric group of size n, and it is represented as Sn or Sa. Note that Sa and Sc might appear to be different. So we prefer the notation Sn, which only deals with the size of the groups. So as we have already observed, only the size matters. So we now look at some representations of Sn and how it behaves somehow. How it behaves. And so now we look at the representation of Sn and how it behaves. See, first of all, we have seen that as the set doesn't matter over here, only the size matters. We assume that the underlying set is 1 to n, this set. This simplifies the task. Every element of Sn is basically a permutation of n objects, right? Any bijection is a permutation of objects. And if it's on finite sets, it's a permutation of few objects, and it's well defined. The sense of permutation and the sense of permutation's combinatrix is the same. So how many elements are there in Sn? Yes, the answer is n factorial. By definition, each permutation is just a renaming of objects. So A1 or 1 becomes F1, where F is a bijection or permutation. 2 becomes F2, 3 becomes F3. They are just renamed over here. and uniquely renamed such that the name is also in this set. So that's what's interesting over here. So if two elements of Sn are there, then fg is operated as g first then f, as in function composition. F of g of x is the same as g of x, and if g of x is y, we find fy, and that's the result of f of g of x. So be careful. A very naive and beginner mistake over here is operating from left to right. Never do it, because in symmetric group, as it's a function group, although this looks like left to right, operated from right to left. Be careful. So we look at a special symmetric group, the easiest one. Firstly, note that S2 has a size 2, and you can show that S2 is cyclic, and S1 has size 1, so it's of no interest. So S3 is our first symmetric group, which is of interest, and it's the easiest one. So we label two functions over here. X is basically 1 goes to 2, 2 goes to 3, 3 goes to 1. This notation is basically a bit transitive. So it states 1 is going to 2, 2 is going to 3, 3 is going to 1. So we have something like a cycle over here, 1, 2, 3. And Y is 1 goes to 2, 2 goes to 1, and 3 goes to 3. So both of them are in S3, right? It's easy to see. So we now want to prove that all other elements of S3 are basically compositions of X and Y, and with the identity, of course. Firstly, note that XY is 1 goes to 3, 3 goes to 1, and 2 goes to 2. YX is 2 goes to 3, 3 goes to 2, and 1 goes to 1. We have not written over here, but X square is 1 goes to 3. Its X square is basically 1 is going to 3, 3 is going to 2, and 2 is going to 1. And Y square is identity, and X cube is also identity. So we have identity X, Y, X square, XY, and YX. 6 elements, and S3 has 6 elements, and all these 6 elements are basically all the elements of S3. Try it out. So again, we have this property over here indeed, xy is equal to yx square, which we will soon prove, and x cube is equal to y square is equal to 1, and all elements of S3 turn out to be 1x x square, y xy, and x square y. Indeed, x square y is the same as yx. By this property, you can show that x square y is the same as yx. That justifies when we said that this yx and xy are different elements. So let us verify yx square is equal to xy. So x square is 1, 3, 2, 1, as I said. First of all, yx square takes 1 to 3. X square takes 1 to 3, and yx square, in y fixes 3. So it goes 1 to 3, and 3 goes to 3. We are going from this side to this side. Look at it once. So this is true, and we also have 2 goes to 2, as x square sends 2 to 1 and y sends it back, and as it is a permutation, we get 3 goes to 1, because yx square is a permutation, right? It's in S3 because it's closed in a composition. So we have 1 is going to 3, 2 is going to 2, so only 3 remains, and the only possible image is 1. So 3 has to go to 1. But this is xy. 1 goes to 3 goes to 1, and 2 goes to 2. This is xy. We just saw it, right? This is xy. So we have a property over here, yx square is equal to xy, and let's simplify an element in S3 by random compositions of x and y to a standard form. So simplify this thing. First of all, x cube is 1 and y square is 1. So y to the power 4 is also 1. So this is basically xy, xy, x square y. Now xy is equal to yx square. So p is equal to take this xy, and as function composition is associative, make this yx square. So it's yx square, xy, x square y. So again, as it's associative, we take y x cube y x square y, and x cube is 1, so this becomes y1 y x square y. Now remove this 1 and take a bracket over here. It's y square x square y, but y square is 1, so this is x square y. X square y was a standard form for us. But we just saw that xy is not equal to yx, right? So this group is not abelian, and S3 is a group, we know it. So this is the smallest non-abelian group which we have come across till now. Indeed, this is the smallest non-abelian group, and it is the first finite non-abelian group. So we shall soon be presenting examples using S3 because this has a unique behavior and is the smallest non-abelian group. Abelian groups are good, well behaved. Non-abelian groups are not, and we have seen only one non-abelian group till now, which was the matrix group, but it was infinite. Over here we have a finite group, and it's always good to work with finite groups first. So the concept of permutations and compositions is a bit complicated and advanced, and if you are not familiar with combinatorics, it's pretty difficult. So except S3, we won't be dealing much with them. We'll assume that the only group of interest is S3 in our course. But all finite symmetric groups are indeed non-abelian. So by default, the infinite is non-abelian. So you can also all of the finite ones. So you can also show that all of the finite ones are non-abelian if you are interested. However, we'll be providing you with some materials regarding permutation and symmetry in the course and its subsets as well. So you go through them and do feel free to ask doubts in the Q&A session or consult your mentor. So our talk is over for today, but before we leave, let us summarize what we learned today. To briefly recall set theory and sets, then we define groups and some related terms like subgroups, order, etc. We devised a few theorems and results to relate these terms like order of elements defined, order of groups, and so on. Next, we looked into examples of groups of different types like finite abelian, finite non-abelian, infinite abelian, and finite non-abelian groups. So thank you very much for attending this talk, and let's meet at the Q&A session.